Friends, Romans, geometry students, lend me your ears. Welcome to lesson 12.2. We're talking about surface area of prisms and cylinders today. Here's some new vocabulary for you. Make sure you understand those terms by the end of this lesson. Go back in your book and review those terms as necessary if you don't know what those things are by the time we're done. Let's check out some definitions here to start this lesson. So 12.2, surface areas of prisms and cylinders. Here I'm starting off with some examples of prisms. I'm not going to have you try to draw all of these here, but I'm going to refer to these as I describe what things are. Definitely a lesson we want to see lots of pictures with in terms of helping us better understand what things are. So a prism, what is a prism first of all? Well, it's a polyhedron. Remember, a polyhedron is made up of all polygons. There's no curved parts to them. So it's a polyhedron, no curved parts, no curved faces are allowed, with two congruent faces, and we'll call those faces, they'll be the bases that lie in parallel planes. So on these pictures, just to make a little more sense hopefully, I'm talking about this would be a base, this triangle part right here, and what's parallel to this triangle part? Well, this triangle part, and these are also congruent to one another. So here's a base and here's a base. And the rectangular prism or the cube, you could actually use this one and this one as the base, or this one and this one, or the front and the back as the bases. Any one of those would work because they're all congruent to one another and they're all parallel to one another. So I could say, for instance, this one is congruent to this one right here, but I didn't have to choose those two. Usually they're on the top and the bottom, but sometimes they'll rotate the picture around. You have to know they're the parallel parts. Here the bases would be this pentagon here is parallel and congruent to this pentagon here. You're in parallel planes, so here's your B here, here's your B here. Here you've got the hexagon. The cube you could use right and left, front and back, top and bottom. Any of those combinations would work. But here, this doesn't happen to be, it looks like it's not a regular hexagonal prism. This one might be a regular pentagonal prism. This looks like this might be the same all around here, but not so much with this one, I don't think. This could be an equilateral triangular prism as well. But from there, I do want to show you something in the book here. Go up a little ways from there. There we are. And so I'm not going to have you draw these pictures in your notes unless you want to. If you'd like to include them, totally fine. But let's just talk briefly about what we see here. So we've got these parallel planes. You have a base here and a base here. Here you'd have a base here and a base here. You can have a right rectangular prism. This one happens to be rectangular because all the faces are rectangles. The bases are also rectangles. That's what makes it a rectangular prism, because the bases are rectangles. This is a triangular prism because the bases are triangles. Here the height is straight up and down. They can have slant heights as well if they are oblique. Oblique just meaning kind of tilted in a geometric sense. So a right rectangular prism goes straight up and down. It's perpendicular here to the bases. So these edges, they go straight up from one base to the next, perpendicular, in other words, to the bases. The lateral faces are the faces that are not the bases. It's going kind of around the shape. Here the lateral faces would be these blue parts going around the shape here. The lateral edges are the edges that are not part of the bases. And so just know those terms, understand those terms, go back and review if necessary there. But that's what we got going on there. Let's define a couple more things. Surface area, you definitely want to know what that is. And if you're one of my students, we very likely have already had an introduction to surface area in volume to kind of overview this chapter, chapter 12. But this is going to go a little more in depth now. So you might see, for surface area, you might see S, A, you might see S period, A period, or you might just see the letter S, capital S. So know those things in this chapter will stand for the surface area. And what is a surface area? Well, it's the sum of the areas. That would make sense. It's something dealing with area, but it's the sum of the areas of all the faces. So on here I'd be finding the area of this triangle, or this rectangle right here, this one right here, that rectangle, this rectangle right here, and these two bases, these triangular bases, and I would add all those faces areas together. That would give me the surface area of that total thing. Same idea holds with all other prisms, with all cylinders as well. The area of the surface is the surface area, the area of the total faces all put together. And the lateral area, which we might refer to at times as LA or L period, A period, is going to be the sum of all the lateral faces, and by that I mean that no bases are included. No bases are included. So here with this triangular prism, back to what we were talking about here, the lateral area would be everything but this one and this one. It would be this rectangle out in front, the one kind of to the back right, and the one to the back left. You would add those three rectangles together, but not this one, not this one, not the areas of those. Now let's check out theorem 12.2 from this point. So here's one of the big things to know. I don't want to go to example 1 quite yet. I'm going to include this down here. So surface area, or SA, we can refer to that as, of a, this has to be a right prism. So surface area of a right prism. This is theorem 12.2, by the way. So we are talking about that here. This is a really big, important concept, so I'm going to box that in. This is one of the biggest two things for this lesson, is knowing that this is the case. So you have the surface area, S, is going to equal 2 times capital B. Capital B standing for, we talked about this in our intro notes, so I'm not going to write it again here, but capital B standing for the area of the base. You may want to make a note of that. And P standing for perimeter, and H standing for height. You know what? I think I am going to make a little note of each one of these things here. So in a different color, this is the area of the base. Let's write that down. Area of the base. That's what capital B stands for. It may have been a little while since we've done these introduction notes here. This stands for the perimeter of the base. And then right here, the H stands for the height. And then this pH part, this whole thing together, pH is going to equal the lateral area. Because it's taking the bases and subtracting those or getting rid of those. This is just a lateral area part. Now why does this work? Why? Let's just think about why this works before we move on. So if I were to find the area of the two bases, going back to this one, I'd be finding this part right here and this part right here. Okay, so that gets me, of the 5 faces I have here, that gets me that part and that part. I could find the area of each one of these rectangles separately. I could find this as doing length times, or width times height, however you wanted to think of that. The length here, the base times the height of that rectangle. You could do the base of this one times the height of that rectangle. You could do all those separately, but doing perimeter, which would be all the way around, doing that times the height does all 3 of them all at once. If you did the perimeter of a pentagon, it does all 5 of them all at once, all 5 of these rectangles here, here, and so on. If you did perimeter of a hexagon, it would do all 6 of the rectangles that would be made, and do all those all at once. They'd be taking all the lateral area faces, the lateral faces areas, taking those with pH, putting them all together, and adding them together with 2 times the area of the bases. There's 2 bases, so we do 2 times B instead of just a plain old B. So pH is the lateral area, H is the height, P is the perimeter of the base, B is the area of the base. Moving on from there, let's check out an example. So on these ones, we're going to find the surface area. We'll use abbreviation for that. So I'm going to have you draw a picture here. Start by drawing a rectangle. We're going to draw a rectangular prism on this one, but start just by drawing a rectangle. And then a couple different ways you can approach this. This is the way I tend to do these myself. I've just gotten used to doing it like this. I go back at the same degree measure, same measure, well, like 45 degrees-ish or so is what I've done right there. And I'm just going to go back, connect those. You can also do this. You don't have to draw both pictures here, but you could also draw two congruent rectangles, one behind the other, as long as you're using pencil, because we're going to have to erase some of these marks. And then you could connect the points here, here, and here, and here. That will get you your rectangular prism. I'm just going to go down from here, draw a point right there, and I'm going to draw the dashed lines in right away. So I just went straight down at a 45-degree angle there, made a little dot, and now I connect those, and that does the same thing for me as I did in this way. You would just have to make some hidden lines here to make that a legit picture. And so from here, let's draw in some measurements. Let's say this is 16 centimeters, this one's 4 centimeters, and the height is going to be 9 centimeters. And so what's the formula we're using? Well, let's go back to here if we forgot. The surface area is 2 times the area of the bases plus the perimeter times the height. So first of all, let's determine what our bases are. Using a different color, let's call the top and the bottom the bases. These are parallel parts. They lie in parallel planes, this rectangle and this rectangle, and they are also congruent to one another. So that fulfills the requirements for the bases for the prism. So we're going to use this and this as our bases, and we're using S equals 2B plus P times H. So B is going to be, looks like a rectangle would just be the little base times the little height of that rectangle there. It's going to be 16 times 4 would be the area of each base. Now the perimeter, we would take 16 plus 4 plus another 16 back here plus another 4. You could think of that as 16 times 2 plus 4 times 2, but I'm going to write the whole thing out, and let's do that for now just so that we know where that comes from. That's just the perimeter of the base, 16 plus 4 plus 16 plus 4. And we multiply that times the height. The height is just the part that's connecting the two bases. So here, so the height is 9 right there. So here I have 2 times 64. This becomes 40 right here, and this becomes a 9. I can multiply this out. I'll get 128 times, it's going to be 320 right there. And so doing all that, I'm sorry, I meant to say 360 right there. I was thinking that was an 8 for some reason. I don't know why. So 128 plus 360 would give me 488. Now this is the surface area. Area is always in units, and we have centimeters here as our units. So centimeters in this case, centimeters times centimeters. We're multiplying centimeters times centimeters. That's centimeters squared. So we have 488 centimeters squared for the first part of example 1 here. This is still a prism here, just as it's going to be over here. We're going to draw a triangular prism for this one though, and we'll make it an equilateral triangular prism. So I want you to draw an equilateral triangle. I'm looking at it on a little bit of an angle, so I'm kind of tilting it down as if you were looking at it on an angle there, and then come straight down here. This is looking just like I had right here. I'm trying to just recreate this triangular prism basically. And so connect that right there. I know that this is going to be congruent to this, so you can, or you could have drawn a triangle here and a triangle here that's congruent, connected them, and then erased. I'm just going to go straight down though. I'm going to have, I know my vertex will be right about there, and if I go straight down from there, I have a vertex there, connect those with dashed lines, and that gives me what I'm looking for. And so let's put this on the picture as well, that this and this and this are all congruent. That will let you know it's an equilateral triangle, and I'm going to tell you that the side length is 6 inches right here, and that this is 10 inches right there. And so with our different color, let's label this with a capital B. This is my base. This is my parallel and congruent base right there. And so I can use the formula for the surface area of prisms based on that. So I have S equals 2B plus PH. Let's plug in what we know. I know that the base, well, that's a little tricky here, but I know it's the side length. I had this formula for equilateral triangles. It was side length squared times radical 3 over 4. And so I'm plugging in 6 for my side length. I have 6 squared times radical 3 over 4. So I replace B with the area formula that works for it. Here, the area formula for a rectangle is just base times height. Little b for base there. Little base times little height would be 16 times 4. But this area a little more complex, but we have this shortcut formula, so we can use that. Now, what's the perimeter of one of these bases? Well, it's just 6 plus 6 plus 6. So let's write that down. 6 plus 6 plus 6. Yes, I know that's the same as 6 times 3, but just so we get the idea of that perimeter, we're adding the sides. We're summing up. We are adding the sides together. Times the height here is 10. Let's make a little notes of, I think this one was pretty straightforward, but where this came from right here, let's make a little note of that up here. This is the shortcut formula, s squared radical 3 over 4 for equilateral triangles. That's where that value came right there. Pardon me. So let's simplify now. We've got 2 times 36 radical 3 over 4 plus this will be 18 times 10. This I could reduce down to, this would be a 9 and a 1, so I could say that's the same thing as 2 times 9 radical 3 plus 18 times 10. Now I can do my multiplication here. I'm going to have 18 radical 3 plus 180. This would be an exact answer. You couldn't combine a radical part with a non-radical part, so we could say, giving an exact answer, this would be the final answer. This in inches squared. If you approximate this though, put this into a calculator, 18 times rad 3, that's about 18 times 1.7, and that ends up being about 31.2. 31.2 plus this ends up being 211.2. This is in inches again, this is an area, so inches squared. So exact answer is the top one, approximate answer to 1 decimal place is what I decided to go with here, is the bottom one. Just make sure you check what they ask for. If they ask for 2 decimal places, use 2. If they ask for 3, use 3. If they ask for 10, use 10. If they ask for 1.5 decimal places, you can laugh at them. That's ridiculous. But yeah, it should be a whole number. Okay, so a cylinder now. Let's get to that. We talked about prisms. Now we're going to talk about cylinders to finish up the lesson here. So it's a solid. Now it's not a polyhedron because all of these edges or all of these faces have curved edges. Some of them have curved edges at least. So you've got, this is a soup can, a thing that comes to mind for me when I think of cylinders that I see in everyday life. A water bottle, this general part except for this top part is generally a cylinder here. So you got these circles right here and here that are again connected here and here. Here you've got a circle here and here connected straight down like that. So it's a solid with congruent circular bases this time. Bases must be circles if you have a cylinder. Congruent circular bases that lie in parallel planes. And this is the other big guy for this lesson, so I'm going to box this in. It's the surface area of a, we're just going to deal with right cylinder, so straight up and down, perpendicular, bases are perpendicular to one another. So surface area of a right cylinder, this is theorem 12.3. And we can use the same formula actually. So we can start with this. We can think of it like this. It's 2b plus ph because you still have bases. Just like this and this were pentagon bases, the same idea holds. We're going to have the area of the base, 2 bases here, times the lateral area part. But we have a different way to write that, or an equivalent way to write that makes more sense, or is the way we need to think about it when we consider cylinders instead. So 2b plus pH, which becomes, so we can say this, or equivalently, this is really the way we need to think of it. My bases are circles. So think of it like this, and I do want you to draw a picture for this one off to the side. So let's draw a picture. We're going to try to make our best cylinder right here as we can. So I'm going to go straight down there. If you're using a pencil, you can draw another congruent circle as best you can, but these are ellipses the way I'm drawing them because they're being looked at kind of on an angle here. So let's connect those straight down, and if you use pencil, you could erase this like that. If you want another way to draw this, or a way that also would work, I sometimes draw mine like this, where I'll draw circles, and then I'll draw a half circle there, half ellipse, and then I'll just connect that part there. So that's a different way to draw it. That's typically how I draw mine, but either way is fine. These aren't perfect. I'm not looking for perfection right now with the notes. I'm looking for that you got the idea down. So this, or equivalently, I should say there, so equivalently, well, what is the base? The base is a circle, and in a different color, let's put that. You've got a B here, this is a B down here. And since the base is a circle, we know the area of a circle is pi r squared. So that's where this next part is going to come from, 2 pi r squared. 2 bases, 2 circles, 2 pi r squared. Plus the perimeter of the circle here, the perimeter would equal the circumference. Circumference with a capital C, that's what that stands for, is 2 pi. That's supposed to be an r. There we go, that's better. So perimeter right there is the same as circumference, which is 2 pi r. The base area is pi r squared. And so the p I can replace with 2 pi r. And we have that still times h. This is really the way to think about it. So this is what I want you to know rather than this. But you can think back to this. It's the same idea as with prisms. It's still 2b plus p times h. So the idea remains the same. It's just that we use pi and r because we're dealing with circles here now. And so where does r come from? Where does h come from? Let's finish this up here in the picture. This would be my radius, my little r, and the height would be from here to here, straight up and down, we're saying is the height, the h. Right, so from there, let's check out a couple examples. So go back, rewind, refresh your memory, review that as need be. Make sure you understand the concept. If you remember this concept, or if you know that the concept is just 2b plus pH, you can derive the formula from that. It's a lot easier to remember the formula based on that. But example 2, let's draw a cylinder here. So I'm going to go with the way I normally draw cylinders. I'll usually just draw an ellipse to represent my circle. I'll go down like that, and then I will make half of a circle or half the ellipse there, and I'll make the other half dashed. And again, you can draw, you don't have to draw both here, but you can draw 2 circles, connect them, and then erase the little parts here to make that part hidden. Either way will work. I don't need both ways though, so I will get rid of that for now. Okay, so I've got here, let's say I give this information to you, that the height is 8 meters and the radius is 4 meters. And I'm going to tell you that that's perpendicular there, so therefore we know it's a right cylinder. So we can go back to the formula. I'm not going to use this, although this is the idea. I'm going to use this instead because that's how I really need to plug things in. So I have S equals 2 pi r squared plus 2 pi r h. From there, plug in your values. You've got your radius of 4, and you've got your height of 8. So that's a pretty straightforward problem once you know what the equation is. We need to get used to giving both exact and approximate answers. So exact answers will be left in terms of pi here. You would have 16 is 4 squared, and then 16 times 2 would be 32. So you have 32 pi, and then over here you're going to have 2 times 4 would be 8, and 8 times 8 would be 64. So you have 64 pi right there. Now adding these or combining these together, you have 96 pi. So this is an exact answer. If you were told to give an exact answer, you would be done. You would say that your answer is 96 pi meters squared. However, we should know how to get this as an approximate answer as well. If your calculator has a pi button, that's definitely what we should be using rather than 3.14. 3.414 is rounded off a bit too much in my opinion, but we're going to use this now instead. So my calculator has tons of decimal places. That'll give me a really good approximate answer of 301. We'll go to 2 decimal places for now, 301.59. So 301.59. So use that pi button on your calculator rather than just typing in 3.14. Gives you a better answer. Okay, so these would be exact values, approximate values. Let's do one more example here before we move on to our final idea. I had said cylinders were our final idea, but there's actually one more thing I want to talk about briefly after that called nets. So on this one, let's draw a kind of a wider, fatter, you might say, cylinder. So like this. And we're going to say that my height is, in this case, my height is unknown. Oh man, I don't know the height. So a question mark there. I do know that all the way across is 19 inches. And I'm going to tell you that it's given, so here it's given the diameter is 19 inches. And we also know that the surface area, I'm going to tell you, is 925.2 inches cubed. We're going to try to find the missing value. We're going to try to find how tall or how high is that. So find the height. Or in other words, find h. So how can we do this? How can we solve this? Here's my solution. So I know that the diameter is 19 inches. So since d equals 19, how can I find the radius, which is what I need for my formula? Excuse me. I know the radius is going to be 19 divided by 2. I'm just going to cut the diameter in half. That would leave me with 9.5. Let's put that in our different color right here. That's something that wasn't originally in the picture, but that I can determine based on the information given in the picture. So 9.5 inches. That's important, not a final answer, but it will allow me to get to my final answer. So I can say at that point, therefore, I know that the surface area, I'm going to use the formula with just the general way first. So S equals 2 pi r squared plus 2 pi r h. Your S value is right here, 925.2. I'll use parentheses as I plug stuff in here so you know that it was coming from up here. So this value gets plugged in right here. Your radius, 9.5. That's going to go right there. And also right there, it shows up twice. And the height, well, we don't know the height, so we're still calling that h. I don't know what that is, but I can simplify this here and I can solve for h, get h by itself with what I have left. So I've got 925.2. 9.5 squared would be 90.25. And then 9.5 times 2, that gets you back to your diameter, would be 19 pi. So you have 19 pi h. Pi times d is the same as 2 times pi times r. 2 pi times the radius is the same as pi times the diameter. So we have 925.2 equals, this times 2 would be 180.5 pi, we have that there still, plus 19, I'm sorry, I left out something important there, the pi, so 19 pi times h. So from this point I would want to subtract, I'm trying to get h by itself. Remember, pi is just a value, it's a constant value, it's 3.14159, 265, and so on and so forth. So that times that 3.14-ish can be subtracted from both sides. So again, I'm trying to leave this as an exact value as long as I can. So I have 925.2 minus 180.5 pi is going to equal 19 pi times the height. Now to get the height by itself, I can simply divide by the value in front of that, 19 pi. So if I divide both sides by 19 pi, and divide this by 19 pi, that will cancel here and here. On the right side, I'd just be left with h. And then if we type this into a calculator, let's get that calculator out, and let's do that right now. So I'm going to have 925.2 minus 180.5. My calculator knows order of operations, so it's going to take this times pi first. It's smart. Make sure your calculator is smart like that too before you would move on. So that's what the top value is. So that's what the numerator is, 358.14. I need to divide this by not just 19, but 19 times pi. So I need to put 19 and pi in parentheses, otherwise it's going to divide by 19 and then multiply by pi, instead of multiplying pi times 19 first and then dividing the value by 19 pi. So let's put 19 times pi in parentheses here. Okay, so that will give me 59.69. Now I'm going to take the value I had, divide it by this, by hitting equals. Okay, so very, very close to 6. If we round that to 2 decimal places, it would be 6.00. So we've got pretty much 6 inches right on the money there. So approximately 6 inches for the height. And so we have successfully solved for h from there. These kinds are a little tougher, a little trickier. You have to get h by itself. If you round it off here, but you rounded off and used enough decimal places, you would get this value in the end. Better to leave it in exact terms, though, as long as possible till the very end. And there's one more thing. We're going to talk about some nets here. So I actually want to show you a video, a very short video, to go along with this, to show you what nets are and how they come together. We may have already created nets at this point. You had the regular polyhedra, where we had from lesson 12.1. In lesson 12.1, you made these shapes, or we looked at these shapes. You may have, if you're in my class, we may have made these already at this point. So we had the nets. They were the unfolded parts. The nets were the unfolded parts. And then when we folded them up, we made these regular polyhedra by doing that. But if you go to some cool websites, they'll show you the nets being folded up and creating the solids in action. So here I've got that, and I'm just going to kind of skim through this. I'm not going to play the whole video here, but I'll keep talking in the background. So you've got this 3D shape that's going to be made with its two-dimensional net. So if you fold along the edges, here it shows you, oh, very nice. It makes a cube. You fold along the lines that were there. They're a little tough to see, but we've got something like that. So as they continue here, it looks like they're giving a little test here. What shape do you think you could make based on this net? So if you fold that up, you fold that up, you fold these up, it looks like that person got it wrong. They clicked rectangular prism. It's not that, because you fold up the triangles. These are going to be the parallel parts, this triangle and this triangle right here. Notice how that and that would be parallel. Kind of got this tent looking shape, but you have these rectangles as the other parts. Well, let's see. I think we'll just go through this as well, and this is a good little test. So what do you think? Is this a square base pyramid, cube, triangle? Yes, you have a square for the base here. You fold up the sides, boom, there's your square pyramid right there. Boom, I'm like John Madden, boom. All right, do you know John Madden? If you play Madden, NFL type stuff, you got that there. Okay, what's the basis here? This is going to be parallel to this part when you fold it up. It looks like they got the wrong thing there. It's not a hexagonal prism. Yeah, it's octagonal prism. Okay, so we fold up all the sides. It would look like, look like that. So there's a net in action being folded up to make a different shape. They got, how many faces does this have? I don't think that's what we're too concerned about right now, but you count up one, we count all up, we'd have 10. Yes, okay, so I'm going to stop that there. How many edges? You could count up the edges too. That was the previous lesson. And so that's what I'm going to show you with nets. So if you want to draw some examples from nets, you can. If you want to look also at page 729, you can see some more examples of nets in your book. I'll briefly show you what that looks like here. So here they have a net of a regular hexagonal prism. They fold this up, you get something that looks like that. But if you look at that video, or you can just Google search yourself where you're folding nets. How did I type that in? I think I typed it in as video showing nets folding. If you want to check that out, this is what came up for me towards the top of that search. Some pretty cool stuff there to help you visualize what's going on. So that's it for this lesson. Hope you found that helpful. There's some trickier examples with ones like this, remember. Just keep it exact as long as you can to solve for the missing parts. And leave things in terms of pi as long as possible, and then approximate from there. Use the pi button on your calculator. On Prisms, the same idea holds. For Prisms, it's 2b plus pH. For cylinders, same thing. It's 2b plus pH, but the b is pi r squared. It's the same thing as the area of a circle. P is a circumference, pi r, 2 pi r. Okay, have a good day, everybody, and I will catch you guys later.